Okay, hey everyone, welcome to lecture 25. So last time we finished talking about parallel repetition. So we discussed what is known about the rate of decay for the case of two players. And then we moved on to discuss the limits of soundness for a given set of parameters, both for PCPs and IOPs. And we saw that in the limit, we can rule out a really good soundness just by increasing alphabet size or round complexity. And we saw that there's some sharp threshold that says if your soundness error is too small relative to query complexity and proof length, then something bad happens. That threshold kind of justifies partially the sliding scale conjecture as an optimistic goal for an ultimate PCP. Today, we're going to shift gears and sort of talk about it's like a bit of a standalone topic, which has to do with the goal of sublinear verification for any computation. Okay, so we have talked about sublinear verification at various points in the class, and we've seen how to achieve sublinear verification via PCPs and IOPs for specifically machine computations. Okay, and more generally, we discussed that sublinear verification is achievable, at high level, if and only if the description of a computation is shorter than computation itself. Okay, informally, computation is structured, right? Because otherwise, by the time the verifier is done reading what computation it is checking, even though it may have small query complexity, or it will have maybe other benefits of engaging in a probabilistic proof, shorter verifier time is not one of them, right? Because if just to figure out what computation it's checking, it will have invested amount of time which is proportional to computation itself, well, that's not savings in verification. And so whenever we discussed the goal of sublinear verification, we talked specifically about computation models, typically machine-like, that would allow reading some short description that describes a long computation. Right, but what if we want to achieve sublinear verification for literally any computation? This, for example, should include ones whose shortest description is the computation itself. For example, think of it as a random circuit, right? A random circuit with high probability is incompressible, and so there's just no shorter description than just saying, here's the gate 1, it's attached to like this other gate and this other gate, here's gate 2 is attached to this other gate and this other gate, and so there's no way to kind of describe this computation shorter in the circuit itself, right? Now, this seems like a bit of a non-starter, because we just argued that we can't expect it. But, we are in charge of modeling, right? And we can try to kind of change the setting to try to still have some to be meaningful, and yet somehow allow for us to kind of smuggle in sublinear verification. So this brings to the setting of so-called holographic proofs. Here, the term holography is, I guess, in my opinion, is a bit of a cool sounding but not very descriptive historical term. And it comes from the 90s. And essentially, it can be thought of as basically considering an offline-online model where in the offline phase, the description of the computation is encoded into an oracle, okay? And in the online phase, the PCP or IOP verifier, rather than being given as explicit input the description of the computation itself, it is given this encoded description, okay? And the idea is that it's okay because it's going to be able to reuse and check multiple statements with respect to different inputs to the computation. So you can somehow amortize the fact that there was this one-time offline cost at the beginning, right? So at some point, somebody has to go over the computation, right? Because information theoretically, that has to be kind of processed, all right? So we're going to rely on this kind of, let's call it offline trusted phase that produces some output that we can then rely upon multiple times during the online phase. And in each of these online verifications, ideally, we can achieve sublinear verification, okay? So this is kind of the high-level mental picture. And today, I'd like to explain how this is formalized and how we can actually, it's actually not that hard to have a feasibility result that showed this is possible. And I'll point out kind of what is known about this. The state of the art is maybe outside the scope of today's lecture. Any questions about the motivation? Again, we want to shoot for like sublinear verification for all computations. So see, there's a question here. Is another word for holographic? So the question is another word for holographic transparent? I guess yes and no. So like in the 90s, before the term probabilistically checkable proof was, let's say, I don't know, rose as the preferable term for PCPs. Actually, first terms given to PCPs were either transparent proofs or holographic proofs. And this particular setting with an encoded description of computation was actually not given an explicit name. It was just basically called transparent proofs with encoded theorems, because you can think of it basically computation as basically being the theorem that is being proved, and you want to kind of encode the theorem itself so that you don't even have to look at the theorem during the online phase. And then for other historical reasons that I'm not sure I really understand, once PCP kind of took over as the main term, when people kind of pointed out, oh look, a certain proof system has the property that if you encode the statement, then you don't have to work as hard as reading the whole statement, then this work was called like holographic. And this was maybe more of a feature of the early 2000s already, maybe like 10, 15 years later, and it kind of stuck. So I was just before today's lecture, I was trying to dig up some one place that specifically connected holographic proofs to encoded like explicitly, and it only happened kind of somewhat by inertia in the 2000s. And yeah, I don't like this term too much. I mean, I like how it sounds, but it's not descriptive at all. What you should have in mind is really like offline and online, and the offline thing gives you a chance to encode and kind of look information theoretically at the whole description. All right, that's my explanation for the term. Sorry, it's not very satisfying. All right, any more questions about the motivation? All right. So now, in order to have this offline and online separation, we need to somehow decide what is the big thing that we don't want to read online, right? So this leads to the notion of index relations and languages. So this is basically a situation where you're going to take what used to be the instance and you're going to split it asunder into the big part and the small part. And the big part, we call it the index, okay? So now, rather than looking at binary relations, we look at ternary relations. And kind of I is this big sort of description thing that describes your computation. And then X is like the online input that shows up later. I'll give you an example in a moment, but let me just kind of formally define. So an index relation is a set of triples made up of an index, an instance, and a witness, okay? This gives rise to an index language, which is just the index with sort of instance pairs that are in a relation. Also, by the way, you can also talk about index languages without talking about index relations if you want, if you don't want to talk about the witnesses explicitly. And similarly to the notation we used in the past, given an index instance pair, you can look at the valid witnesses for it. Okay? So what are some examples? So let's look, for example, at circuit satisfiability. Now, if you don't care about splitting the circuit into like if you're not going to have sublinear verification, there's no reason for you to talk about separately, let's say, about the circuit and the circuit input versus the witness, right? You just hard code the input into the circuit and you just talk about the circuit being satisfiable or not, okay? But now in this setting of indexed relations, we're going to say, no. Like I have fixed the circuit. That's the big part that I process in advance, okay? And maybe now I'm interested in input X. Maybe later I'm going to be interested in input X prime, X double prime. And for each one of them, there might be like, some different witness, and I'm sort of wondering about the satisfiability when you fix to that one circuit this x or this other x prime or this other x double prime, right? So let's think of an example even more concrete. Let's say the circuit is, I don't know, okay, I'm gonna give a structured example because I think it will it's just easier to come up with it. Let's say that the circuit C is like some really long hash chain, okay? And you don't want to talk about it online. And let's say maybe the hash chain is, I don't know, like hard to compress because maybe there's a different hash function at each round, whatever, okay? Maybe different round constants for each one. And the statement you're proving is you know a preimage, okay? So W is the preimage and X is like the statement that you wanna check, right? And yeah, like maybe for this image I want to prove a preimage, for this other image I want to prove a preimage, but the circuit is the same, okay? So I'm happy to kind of share the index across these instances, okay? And similarly, you can go back to a number of other NP relations that, like for example, quadratic equations. You could say, okay, well, the actual quadratic equations are those, but then my assignment, I think about it as like some small kind of fixed variables that I fixed right now, and the rest are kind of free to be a witness, okay? And so I ask, this satisfiability. And before, when we talked about these things, we didn't really distinguish between X and W because you could think of X having been hard-coded into the equations themselves, right? For rank 1 constraint systems, similarly, you can the index is the sort of big matrices that describe all the constraints, and the assignment is going to be the concatenation of the small number of variables that are you of interest, and the rest is kind of the free witness, okay? So all of these, and so this is kind of a bit of a choice of how you split up your language, right? But these are, I think, some particularly natural ones. The point being is that with index relations, index languages, you're kind of telling the proof system, what you consider to be the big fat thing that needs to be processed in advance, and what is the smaller online thing, right? Does this kind of modeling make sense? Okay, great. Yeah.
Quick question. How are you deciding where to like split X and W in these like last two examples? Because it seems like they're both like for QE set, it's like an input. Both X and W are input to the polynomial.
Yeah, you can either, so this is again a modeling choice. You can either say that you fix the size of X and you stash it in the index, okay? And you say, I'm only going to consider inputs of size 10, and X is forced to be of that size. Or maybe you just leave it free. Whatever size it is, and the remaining variables are considered the witness. Both have been considered. Sometimes there are technical reasons why you may want to fix it. Other times there is a proof system that actually doesn't care that you fix it in advance and is happy to be decided on the fly. Okay? Generally speaking, like it is worth doing this split only when you are interested in X that is significantly less than a total number of variables. Otherwise, by the time kind of, like if X is, I don't know, n over 2, then are you really saving so much? Like M and N usually are comparable, so are you really saving, are you really having any savings by sort of pre-processing the equations, okay? Yeah, good question. More questions about modeling here? All right, so now we have this model. We can actually try to write down a definition of what is a holographic PCP. It's pretty simple. So the main thing that happens is that you have not just the prover and the verifier, but you have a third entity, the indexer. Okay, it's called the indexer. And of course, rather than being about a language, it's about an index language, right? Because the proof system needs to know how you decided to split your instances. And the conditions are as you would expect. So in the good case, it says if you take an index and an instance that are in the index language, then if you compute the encoded index and the correct proof, and you give both to the verifier, it will accept, let's say, probability 1. Okay? Crucially, notice that the verifier receives as explicit input just X, okay? Not the index, because again, it cannot afford to read the index, but maybe by designing the PCP correctly, it will kind of get the benefits of knowing what index is by querying the oracle at a small number of locations, okay? Now, soundness is important to understand that when we consider like the bad case, the indexer is trusted, okay? Like we're saying the verifier has oracle access to the correct encoded index and whatever proof the prover decides to give it, okay? But crucially, this pre-processing, it is something that we can rely upon. We know has been done by a trusted entity, okay? So you can think about it as the verifier itself, or maybe something that, you know, is available to everybody, and then if you don't trust it, you can redo it yourself, okay? But yeah, so the soundness, only the proof is bad, okay? So diagrammatically, it's you can think about it like this. The indexer works once, only once per index. Now you have this encoded index. And online, any number of times, you know, for example, for this X, you produce a proof and the verifier kind of decides this question here. Some other time, a different proof is generated for a different X prime. That would be about checking this statement, and so on and so forth. So this kind of one-time cost can be reused any number of times, okay? And now, crucially, because we have this new ability to encode indices, we're going to charge the proof length, not just the PCP itself, but also the encoding itself. So we don't want to somehow smuggle, if we were to not count it here, we could just like write down, I don't know, exponentially large index encodings and make our life sort of unfairly easy, okay? So we're going to be charging proof length on the sum of the size of the kind of encoded index and the PCP, and similarly query complexity will charge the queries to the encoded index and the PCP itself. Again, you know, because if you don't charge that, then you can just read off the entire index and then we're back to square one, okay? And you know, you can similarly define holographic IOPs. I'm not gonna do it, but at this point, sort of, you should be kind of agile enough to write down the definition by yourself. And not only that, you can also write definitions for holographic IOPs that are robust, holographic IOPs of proximity. You can sort of all of these things are kind of orthogonal features that they can coexist, okay? And you know, in the extreme, you can have a holographic IOP that is both robust and proximity, right? So, and such things have been considered. Any questions about the definition? Yeah.
How would you implement the indexer?
Implement in the real world?
Yeah.
Well, we're about to get to it in the next slide. Good question. For now, this is just an idealization. And yeah. So now let's talk about a kind of as always, whenever we're talking about PCPs and IOPs, they're interesting only insofar as they're useful for something, right? And so just like when we introduced IOPs and PCPs, we had to check, okay, cryptography can benefit because look, we can somehow implement the kind of the oracle, the query access to the oracle, right, cryptographically. Similarly here, we're going to see that there is a simple extension that lets us benefit of this preprocessing in the real world. And so while in a PCP, this preprocessing typically referred to as holography, in the cryptographic world, this is typically referred to as preprocessing. So one motivation to study holography is indeed that it naturally leads to so-called preprocessing arguments, okay? So, and analogously to holographic PCPs, preprocessing arguments enable sublinear verification for any computation given a one-time public preprocessing step. So, so pictorially, I mean, I'm not going to define a preprocessing argument system, but pictorially I think it's pretty clear to show. So here it is. You have an argument indexer that gets the index and it produces two outputs. It's like a key pair, okay? A proving key and a verification key. Now, crucially, the proving key, we don't particularly care whether it's long or short. Usually it's going to be long. because anyways it will be consumed by the prover. But the verification key needs to be short. Like now we don't have oracles anymore. We only have like actual strings. So the only thing we can afford to pass on to the online verifier is something short. Okay? So again, you can think about it as some big circuit, even a random circuit, and we'll show in a moment how we actually implement this given a holographic PCP, but right now I'm just defining what is a preprocessing argument. Somehow you're going to preprocess this very large circuit and you kind of come out with like this short commitment to it. It's like a summary of the theorem or of the computation, cryptographic summary. And we produce some output for the prover. And then online, when the particular instance and witness shows up, the argument prover will use the proving key for this index, and the argument verifier will use the verification key for this index, and they're going to talk about it like they normally talk about things, except that now they have this key pair that represents which computation they're talking about. And so in the past, we have seen kind of how a normal PCP or IOP plus a collision-resistant hash function implies a succinct argument. Now we're going to see how, if the thing we start from is holographic, then we can basically change the paradigm and get a preprocessing succinct argument. Okay? Again, all I've done so far, I haven't done any constructions. I've given a definition of a holographic PCP, and then I've given a picture definition of a preprocessing argument. Okay? They're reminiscent of one another, obviously. They both have this offline-online feature, but the crucial difference is that in the PCP world, everything is oracles, and here everything is actual strings. So you cannot afford to send long oracles anywhere. You just have short strings. Okay? Any questions about what is a preprocessing argument? Okay. All right, so we have this implication that we can see now. Okay. So, well, first, let's say everybody has access to the same collision-resistant hash function. You can think about this as a setup, or alternatively, you can think about a slightly more refined model where it's generated by the verifier. It doesn't matter right now. Let's say the collision-resistant hash function is in the sky and everybody knows it. Offline, we would like anybody to be able to compute this key pair for the index, okay? That is reusable any number of times. So any ideas of how we're gonna do this, given what we've done in the past? So what the argument indexer is going to look like? We have a collision-resistant hash function. There's only so many things we can do. Okay, well, look, we are given a holographic PCP, okay? So at the minimum, we should run the indexer for that PCP, okay? That will give us some encoded index, pi 0, okay? Now, our goal is that later on, when the argument verifier will be running, it will be simulating the PCP verifier internally, right? It normally does, right? And that verifier is gonna want to have query access to pi 0, right? So what should we do here so that later it has query access to it?
Will likely compute some form of commitment to it.
Yeah, what kind of commitment?
A Merkle tree.
Right, so we're gonna basically commit to the encoded index by computing a Merkle tree over it. We're gonna get some root RT0, okay? And then we're gonna output the key pair that says, all right, so I'll just stash in the proving key the index itself and the encoded index, why not? Because the prover, then I don't have to ask the prover to recompute this one every time. So this is pretty long, but that's okay. The prover, that's the prover's problem. And this is a short commitment, the verification key, which is just the root of the Merkle tree over the encoded index. Okay? Now, what's the point is because later on, the prover and verifier, they're each going to have access to the respective key. And in particular, the verifier is going to have the verification key that is guaranteed to be the root of a Merkle tree over the correct encoded index. Okay? Why? Because just like in holographic PCP, the indexer here is trusted. Okay? It is a public kind of compressing it's a public cryptographic compressing function that anybody can run on a particular index, and everybody will always get the same answer. Okay, so it can also be rechecked whenever you want. Okay, and so what will the prover and verifier do? Well, they will basically do whatever they did in the past, just in the presence of a second Merkle tree, right? So the prover will compute the PCP for this index, right? And the index, where does it get it? It's inside the proving key. It will compute, as usual, the Merkle tree root over the PCP itself. It will send the root to the verifier. The verifier will say, here's my randomness. And the prover will deduce the query set for the verifier on this randomness. But crucially, again, this query set now is queries either to the PCP or the encoded index, which means that these are either leaves under the Merkle tree root RT or RT0, right? So it will deduce authentication paths for each of these answers, and it will provide the answers and the authentication paths. The verifier will just simulate the PCP verifier, and it will check the answers are authenticated with respect to the correct root. Okay? And again, like RT0 is like the trusted root we have in the verification key, and RT is whatever the prover decided to commit in its first message. So whatever it is, it is. Okay? But that's fine because, again, like we have security for any PCP. So whatever PCP he had in mind, he had in mind. Okay? So it's a pretty simple extension and intuitive, I think. Does it make sense?
So here, when the verifier checks the authentication path, isn't its complexity already linear in the security parameter?
The question is the verifier's complexity linear in security parameter? Yes, it sure is going to be, because we're in cryptography land, right? And even just describing the hash function without doing anything is going to already take me lambda bits, right? But that's okay, right? Because we're not trying to save less than lambda. Lambda is lambda bits. It's 256 bits or whatever, right? Some pretty small quantity. We're trying to save the size of the circuit that we're checking. Like it could be like, a circuit made up of, a billion gates or something. And that's what we don't want to pay online, right? So we're gonna commit to, there's gonna a billion gate circuit encoded in, 100 billion 100 billion bits of PCB. But then we're gonna commit to it away, and I'm gonna store just the root, which is 256 bits. And online, as long as my PCP, my holographic PCP is gonna make a small number of accesses, is gonna run in sublinear time, I'm not gonna be paying for anything that grows proportional to the large circuit that I'm checking. Does it clarify, Shurjit?
Yes.
Okay. Yeah. Good question. Now this is just one setting where holography implies preprocessing. There's variations of holographic proofs all over the place, and somehow with different types of cryptographic compilers, you can get different types of preprocessing arguments. But as a general rule, kind of whenever you can somehow push processing the non-uniform part of your computation to an offline phase, you can try to somehow reusably commit to it, and then that's like a general sort of connection from holography to preprocessing. Okay. Any more questions about this slide? All right, so we talked about holographic PCPs, what they are, what preprocessing arguments, what they also are, how do we go from one to the other. We're just missing where do holographic PCPs come from, right? Here I was just pointing out that that this is a succinct argument. All right, so we have proved in the past that NP has PCPs with polynomial proof length and polylogarithmic word complexity, right? So this was the PCP based on low degree extensions and low degree testing. And in that case, the PCB verifier did not and also could not run in sublinear time because it had to read the description of NP statement being proved. Okay? In that case, it was a list of quadratic equations. Now it turns out that we can kind of go back and modify that protocol to achieve sublinear verification. Okay, so we can prove that the language, the indexed language of quadratic equations has a holographic PCP where the verifier runs in time that is polynomial in the, whatever partial assignment you have. That one you have to pay for, like it's given to you. But if you have some number of variables or equations, you're going to pay logarithmically in that. Okay? And otherwise, these are the very same parameters we achieved last time. Okay? With this, this funny expression was because we were using low degree extensions where the number of variables was like log n over log n. And again, here I'm specifically mean the index language where the index is the equations. We have a partial assignment that's given to me as at the online phase, and I'm asking whether the partial assignment can be augmented to a full assignment such that all of the equations are satisfied. Okay. And note that, for example, through the implication we've just seen in a prior couple of slides, this directly implies a preprocessing succinct argument for quadratic equations where the prover runs in polynomial time, the indexer runs in polynomial time, the prover runs in polynomial time, and the verifier in polylogarithmic time. Okay, that's actually it's like a non-trivial result to some extent. You have a succinct argument where you can preprocess in polynomial time the circuit or the equations, and then during online phase you can run in polylogarithmic time. Okay. So I just want to kind of maybe highlight, why do people care about a sublinear verification for any computation? Well, first, just is of intrinsic interest. I mean, you can have sublinear verification without indexers for structured computations or for any computation with an indexer. So these are kind of incomparable, okay? So when we constructed things for machines, we didn't have to rely on an indexer, but also we were kind of stuck with sublinear verification only for like machine-like things, right? Conversely, like I can go to all computations, but I have to now have an indexer in this offline-online model. So I view it as a sibling to what we've done so far. It is, both are sort of useful and interesting goals. Okay, I wouldn't say either of them is better than the other. But also more pragmatically, when you don't have to make your computation look like having a certain pattern, it's much easier to program. And so, for instance, in the past decade that people have been working with succinct arguments in the real world, one of the, let's say, enablers in the real world is that the types of succinct arguments that were first practical, they actually were in the preprocessing model. So you could express your computation without any regard of how it looks. So you could just basically lay out essentially circuits without thinking about it will look ugly or not, or whether it has any structure. It was much easier for programmers to just basically think of the statement they were trying to prove things about and just like write down like components for it with no attention to those things. This is very much in contrast to, in the real world, programming machines where it's much, much, much harder, especially when you do it efficiently. You want to kind of write out by hand highly optimized machine-like computation is extremely difficult, okay? You basically, most such attempts in the real world have basically reduced to, you do once and for all like a reduced instruction set computer, and then you program that thing instead. But this kind of causes, this is like programming something you've already programmed, so you have like simulation overheads. So like direct programming of machines is very complicated. okay? Like without going through like an architecture, if you just want to actually write down structural computations. So it has been like extremely convenient in the real world and has played like a non-trivial role in sort of not having too high of a, I mean, relatively speaking, not such a high complexity barrier to program actual NP statements of interest. Then there's also other sort of theoretical reasons. There are topics that we didn't discuss in this course having to do with cryptography, like succinct arguments about succinct arguments about succinct arguments. You know, when you kind of make this kind of recursion of succinct arguments, there are specific reasons for why having preprocessing arguments makes that more efficient. And these are things you can prove like formally. So it, you know, plays an important role. But okay, so I stated a theorem. I am actually going to be able to prove this theorem because it's actually not so hard if all you really want is just polynomial efficiency, like a polynomially size index, polynomially size proof. It's not that difficult to achieve holography. So I'm going to explain how to do that as a modification of our old protocol. Any questions about this slide? Okay, so it's been a while, but we did construct a PCPs for quadratic equations many lectures ago. So let me remind you how the protocol looked like. So we had these two hypercubes, one measured to the size of variables and the other one measured to the size of equations, okay? They had these sizes and these are the number of variables, okay? And the prover and verifier, now I've already kind of split the index and the instance, but it doesn't matter. What we did last time was that you would take the full assignment A, so it is the concatenation of X and W, compute the logic extension of it and just write it as part of your PCP. Then, if you remember, the way that it worked is that we had this randomized reduction from m equations to one equation, okay? And so for every choice of that one, we had this basically a way of bundling the equations. We had m equations and we kind of indexed them by tuples in HE to the SE, which by the setting of parameters equals m. And so we kind of index every equation, P1 through Pm, using tuples like this, and we just add them up in this randomized way to get this kind of new quadratic equation that is like a random combination of the old ones, okay? So this was like a random reduction from many equations to one equation. And then we use the sum check protocol to show that that equation is satisfied at A, okay? And why is the sum check protocol here? Because evaluating the equation is actually summing up all the n squared coefficients, and that's a sum. And if we kind of logically extend the coefficients and the assignment is already logically extended, then that's going to be like a sum check over a logically polynomial. So that's kind of what we did last time, and we output all the sum check tables. Now this time, because we've split out the explicit input, we also have to output some input consistency proof. I'm not going to talk about how it looks like. We've seen them already a couple of times. It's just an input consistency proof between that says that X is consistent with pi a in the right domain. So this was kind of what we did last time. The verifier would logically test the logic extension. It would sample one of these randomnesses to select one of these random equations. It will, so now I'm describing what we did last time. It literally computed this random equation, okay? Then it ran the sum check protocol on the extension of its coefficients, right? So it has n squared coefficients, so this is a bivariate thing. And this is basically the value corresponding to the coefficient alpha beta, or like ij, right? So this is a sum check that's going to touches the logic extension, touches these guys. And then you can also check input consistency, which will touch this guy and this guy as well. So this is, if you go back to, I don't know if it was lecture 11 or so, this is essentially this is literally what we did, minus the input consistency, because we hadn't split out X from the equations, okay? Any questions about the protocol? This should look familiar. I mean, it's been a while, but we also did many similar things in the past, in the interim. So hopefully it's not too alien looking. All right, so this was the construction of a polynomial size PCP with a polylogarithmic number of queries for NP and specifically for quadratic equations. Okay, quadratic comes in here because we have like 2 terms of the assignment. Now we are interested in a situation where the verifier doesn't get as input the equations themselves, right? So in particular, now the verifier cannot afford to compute this random equation, right? Because here it was saying, given the m equations, let me add them up using these weights to obtain this new quadratic equation obtained as a linear combination of the other ones, right? So this is something that we cannot afford, okay? In particular, we don't have the equations, like, right? And similarly here, this was the low degree extension of the coefficients of this equation. So that too, we cannot afford. Instead, we will replace that term here with some polynomial that will be written out in the encoded index. So now I'm going to talk about what we put in the encoded index, okay? Now, the encoded index does get the equations. And so what we want to do in the encoded index is do something that is going to help us complete this sum check, right? Originally, what we wanted to do here was evaluate, have a low degree polynomial that is the low degree extension of the coefficients of this randomly obtained equation from the other ones, okay? So here's what we're going to do. First, we're going to think of the equation that we obtain in a random way as a polynomial. So rather than putting in a specific r, we're just putting variables here, okay? So here I take quadratic equations, and I take the quadratic equations as coefficients of a polynomial. So now I have a polynomial such that if I evaluate it at any given point, I will get a quadratic equation, right? So this is what I was doing before. And here I'm just saying, whatever, I don't know what randomness is going to be used later. I just put in variables here for now, okay? And this is just some vector of coefficients corresponding for any r that I put in. I have a typo here. Here it should say f. This is for every f in SE. That should because we have to consider all error in the field. So for any r that I could put in here, it will give me the correct linear combination that I'm interested in, right? All right, so this is basically a computation that the verifier had to do, but now I'm just going to say the indexer thinks about it. But then that's not all we wanted. We actually wanted to low degree extend this equation. So here's how I'm going to do it. I'm going to consider a polynomial that has many more variables, and it's going to be the low degree extension of this polynomial, okay? So I'm going to consider a sum over all n squared coefficients of p hat, okay? And for each of those, I'm going to apply the multivariate low degree extension, for that bivariate function. So that's going to introduce SV variables here and SV variables there. So I have added 2 SV variables. Okay, so now this is has many variables, but whatever. That's a polynomial. I can, oopsie, that should say plus 2 SV. That is a polynomial in SE plus 2 SV variables, and I can just evaluate it everywhere in the field, and I get my encoded index. Okay? And now let's see what happens if that is what the verifier has access to. When evaluated at R, this thing is going to collapse to the correct random equation that I want. Okay? And when evaluated at alpha and beta, that alpha and beta is going to appear here, and that is going to be the evaluation of the low degree extension of those coefficients, which is what I wanted to do here to begin with. Okay? And again, here we're being extremely sloppy because we have just polynomial proof length. So here I've kind of blown up cubically the things I started from, but that's okay. That's still a polynomial. Okay? And that's it. This is actually a holographic PCP. Notice that the verifier never does any expenses operation. It is basically randomly test, that's easy. Sampling randomness, that looks easy as well. It runs sum check. Remember, sum check is easy up to the evaluating the addend at a random point. Well, let's do that. Well, that's just a query to this one. That's a query to this one. And this guy is a query to this one now. Okay? Kind of all the evaluations have been prepared for us by the indexer. Okay? And over here, well, we've already seen in the past that input consistency checks are proportional to the input size. So yeah, this is kind of like the canonical construction of a holographic PCP. Any questions about it? More generally, almost any, sorry, Julius, I'll get back to that. Almost any a PCP or IOP that we've constructed, if you don't care about the size of the indexer being polynomial, you can make it holographic because almost everything we did is algebraic, and you will be able to just kind of push that algebra stuff to the indexer if you don't care about polynomial blow-up factors. It's pretty interesting that somehow kind of as an additional feature, holography is not that complicated for natural constructions, okay? And again, without paying attention to the size of the encoded index up to polynomial factors. Yeah, there was a question.
Yeah, so I was wondering, it seems that we consider sort of the indexer as a neutral party, in a sense. And I was wondering whether there's any natural notions to strengthen that, sort of something along the lines of soundness against indexers.
So it cannot be completely untrusted, right? Because the indexer is really has to receive the correct. Like imagine that if it is untrusted, it receives an index, it discards it and does something with a different index, right? So, but there are ways you can relax the notion of an indexer. For example, you could imagine an offline protocol where you have a trusted indexer verifier and an untrusted indexer prover, okay? Where like some of the production of the oracles are with the help of an untrusted prover, okay? And that also has been considered, though I didn't, work it out here. And kind of similarly to how interaction helps you during the online phase, interaction can be helpful during the offline phase by instead of just considering all possible options, you just kind of ask the prover to supply those, and you may run some checks, and but otherwise, but you're still going to have like this root of trust, like as a trusted indexer verifier, okay? And more generally, kind of anything that you would run online that doesn't depend on the specific input, you can just push off to this kind of pre-processing phase, so that you have to pay for it only once. It's a good question. You should also mention there's been various types of preprocessing that people have explored. The first practical ones were actually not through holography, they were through other things. And they were not super nice because you actually have to trust the preprocessing. Like, it's not like you did it and I can check your work by redoing it myself and I get the same output. The preprocessing involved private coins that had to be discarded. Okay, this is something known as a trusted setup. This preprocessing is kind of the extremely benign kind in the sense that it is a deterministic function that anybody can just rerun and you can just check that you get the same output, okay? I mean not just here, but also the compilation into the argument as well. So that's like basically as good as it gets. It's basically, you can basically have to trust nobody, and in fact, the mere fact that the output of an indexer is in the sky unchallenged, it means like you can trust that many people have like recomputed it themselves, right? It's kind of like, I don't know, when you look into a textbook, you trust proofs to kind of be correct in it, because if not, somebody would have raised a flag before because they were just there. Anybody who wanted to check it could just open the book and read it, right? It would take time, but like then you've checked it and that's it, right? There was no kind of trust beyond that, right? And similarly, it is for these types of indexers and what they imply through CRHs. They are sort of the public kind. Okay, more questions about this construction. I skipped a few steps, but at this point you should be like some serious ninjas with probabilistic proofs. So hopefully, like this kind of algebraic trick should make sense. Okay. We're just basically postponing evaluating things until the online phase, accumulating indeterminates. And each time we accumulate indeterminates, we kind of make the proof polynomially larger, but whatever, it's fine. Okay. Okay. So, all right, so that's a holographic PCP. What is known for IOPs, right? So you can ask, can we improve the proof length by using IOPs instead of PCPs, right? So that was a theme of interaction that we could insist, for example, on things like linear proof length. But now we have like this additional consideration of holography, right? This requires some new ideas, but can be done. So for example, here is a statement you can prove that is analogous to what we proved the linear size proofs for IOPs for 1CS. So for large smooth field, there is holographic IOPs for 1CS, where the proof length, which now counts, sorry, there should be an S here. I'll explain what is S in a moment, which now counts both the indexer size and the communication size during online phase, is linear in this S, and the verifier is logarithmic. What is S? Well, it is just the number of non-zero entries of the matrices, okay? So we're gonna have to read these matrices. Remember, the matrices were m by n, right? But the representation of these matrices is its number of entries, okay? So that's like a third parameter. It's neither the height, neither number of rows, nor the number of columns. That is mn entries, but whatever, like you can have out of an m times n entries, you can have some number of non-zero entries, and you're going to pay for that in your proof length and query complexity logarithmically, verifier logarithmically in that. Okay, that's kind of the sort of correct thing to be measuring things against. Also, without loss of generality, S is linear in m and n at least, but it could be slightly larger. Right? In particular, it could be as large as m times n. But nonetheless, this basically says that in the same regime as linear size IOPs for R1CS, we can have linear size holographic IOPs for R1CS. Okay? And similar things can be proved for quadratic equations, where S is going to be the total number of non-zero entries in the quadratic equations. Which is basically the cost to read them. Right, so we build on our prior theorem, and the main difference is that we had to go from verifier time that is linear in a number of say constraints. Also, we did have to pay a little bit more, right? Because before, because the verifier was reading the matrices, actually there was never any cost in proof length or query complexity in the number of non-zero entries. But now there is, because kind of we have the coded index, kind of remember information about the matrices. And so this, I mean, kind of even given that we have already seen the non-holographic variant, explaining the holographic variant would probably be a lecture on its own. So here I'll just mention at high level that the key problem we need to solve is to design a holographic subroutine for checking linear equations. So it's something like this. You kind of want to check this. If you remember, this was like one of the important subroutines of this protocol. You want to check, given two oracles f and g, that their interpolation over some domain is related by the linear equations of a matrix M. And you want, and so we had some solution back then. It basically, it was a randomized reduction to a univariate sum check, if you remember. And what you want to do is you want to design a holographic subroutine for that task, where the indexer will get the matrix, produce some encoded, basically encoded matrix, and you want sort of the online phase to be not paying for the number of non-zero entries in the matrix. And this is easy if you just pay for m times n, but if you want to make it proof length order in number of zero entries and verifier time being logarithmic in that, then you need to do like some algebraic tricks. And that would take some time to explain. They're related to bivariate Lagrange polynomials. But this can be done, and that is a goal that it's nice to know that in general, making proof length shorter, you always have to come up with some idea. Okay, if you don't care about proof length, things become much easier. But if you start being like linear proof length, then you actually need to think a little bit. Okay. I'm not going to explain further what's happening inside here. I'm just pointing out, where the heart of the matter is. Once you solve this one, you just basically throw it back into that protocol and you get this thing. Any questions about this slide? Okay. Well, today I try to keep it a little bit more light, and so I want to spend, just one slide, retrospectively, because next week there's no class, period, like neither on Tuesday nor on Thursday, and the following week there are class projects, and for those of you that are taking a class for credit, I will be taking attendance to make sure that you are there to support your peers. But because this is so the last, let's say, let's call it a lecture for me, I wanted to do like a bit of a retrospective. So we've kind of covered a lot of things. So we started out with interactive proofs, which should feel like a long time ago. It certainly feels like for me. Introducing basic notions to kind of get started. If you notice, I told you back then, we're going to keep using these things, and we did, like, constantly, right? Things like the notion of arithmetization, soundcheck, logic extensions, right? We also went, pretty far out, studying things like doubly efficient interactive proofs, IP equals P space, limitations on the communication complexity, zero knowledge. We never came back to that. There's only so many lectures I can give, but there are many things we can talk about zero knowledge for PCPs and IOPs also. So then we kind of moved on to probabilistically checkable proofs. Kind of saw how to construct exponential size PCPs with linearity testing, point size PCPs with logic testing. There were important sub-protocols that we kept reusing, like zero testing. So we looked at interactive oracle proofs, which kind of extends both of these models. And one of the main things that we were able to get out of that model was linear size. Okay, it's like this kind of ultimate kind of goal for like a proof length. And so some of the enablers for that was the univariate sum check and the Fry protocol, which was perhaps one of the more technical things we've seen in the entire course. Took a couple of lectures just to describe and analyze, and not even fully at that. Then we kind of moved on to proof composition, for example, to prove the PCP theorem. And that took us on a detour to construct robust proofs, proximity proofs, and show how to combine them together to reduce query complexity. And again, this is really not the end of the story. Proof composition has been used in many other contexts. And on top of that, there are other different types of proof composition that you can go into. And then we've seen, more, let's say, I don't know, let's call them advanced or like miscellaneous topics, something about parallel repetition, sliding scale. We proved some pretty strong lower bounds on the limits of soundness versus query complexity and proof length for PCPs and IOPs. And today we saw holography. At least for now, at least that's it And that's not really everything, but that's really all we have time for. And like, I'm pretty tired of like, preparing these lectures. I'm pretty glad to be done. Yeah, so that's kind of the what we've done. Hope it was interesting. It was probably not easy, but I think you are like with all these things, like it really does give you like some very, very strong foundations for going out there and reading sort of the frontiers of probabilistic proofs, and know what's going on not just locally, but ideally kind of see also some of the I don't know, like texture that kind of or background that lies behind it that connects all of these things together, because they are connected. They're not just sort of protocols in isolation. So with that, I'm going to stop the recording.